Good morning, everybody, and welcome to the CEIA Maths Tutorials Online. This morning we've got Mark Murphy back to do integration. You've met him a few weeks ago to do geometry of the line. And as you know, Mark is a chartered structural engineer, and he's going to deliver the integration tutorial. And integration is the first of our two calculus tutorials, and calculus is a very popular topic amongst scientists and engineers, as it's very useful for all kinds of things, especially dynamic systems. Okay, so I'm going to introduce you now to actually just let Mark take over, and away we go. So, okay, Mark.
Thanks, Eamon. Share my screen with you. This morning we're going to do integration. I suppose 3 weeks ago when I did geometry of the line, it was quite easy to, let's say, show you how I use geometry of the line every day in my engineering career. Not so easy with integration, however, it is used in the background of most computer programs that we use. So look, again, I think 3 weeks ago, I just talked a little bit about my career, and maybe some of you out there are considering a career in engineering. And I remember about 3 years ago, people asked me, do you do much traveling with engineering? And the simple answer is you do, I mean, I've worked in Germany, I've worked in England, I've been to conferences, I've used even in a nuclear power plant up in Finland. So you do get opportunities to travel, I've worked in England, as I say, Germany, and currently working up in Leitrim, which is also quite remote. So there is opportunities. You're not sitting in the office all the time. And my usual week would be 2 days a week, if not 3, out of the office, standing in rivers, looking at bridges, inspecting bridges, and then you do your calculations and you do your documentation back in the office. So it is a good mix. It's certainly not sitting in an office all the day doing numbers. It's not that. It's a lot more than that. There's a lot of meetings. There's a lot of interacting with people. There's a lot of, let's say, surveying and being on site, being active really. And it's definitely, I think, a very rewarding career, right? So if any of you are interested in discussing it further about engineering, drop it the chat or drop an email to Eamon there, and maybe even during the break or the 10-15-minute break that we'll have later, you could ask some questions, So anyway, getting back to integration, the curriculum is quite short for integration. There's only 4 topics that you need to cover. Number 1 is recognizing integration as the reverse process of differentiation. Number 2 is integrating sums, differences, and constant multiples of the form x to the power of a to the power of x, sine ax, and cosine ax. The third one is determining the areas of plane regions bounded by polynomials and exponential curves. And the fourth part is using integration to find the average value of a function over an interval. Now, just from the little survey there, I noticed that 86% of you have not done integration yet, right? Which is good for me, because now I know exactly, I'll take a bit more time maybe at the start and explain integration. So the very first part there is actually, I call it 0, right? Because it's actually not on the curriculum, but it will give you an idea and give you a background into integration. Integration was introduced as a means of finding areas using summation and limits, right? So I'd say that again. Integration was introduced as a means of finding areas using summation and limits. Again, I don't like definitions. I don't like big wordy statements like that. I think it's better to, just go through a few examples and you'll understand it without needing to, understand the wordy definitions. So I just write down here integration. As summation. It's actually a U. Okay, so it is related to differentiation, and it's a topic where you need plenty of practice, right? I suppose the core idea is we can find the area of a shape by dividing it up into smaller shapes whose areas are easier to calculate. We then add up the areas of the small shapes. I'll just say that again because it is the core idea. We can find the area of any shape, right, by dividing it up into smaller shapes whose areas are easier to calculate. And then once we have all those small areas, we can add them all together to get a bigger area. For example, if we had a shape like this, let's draw something like that. Sorry, mine's a bit wobbly. Let's see, like that. Oh, and like this. It's not easy drawing on an iPad. So for example, something like that, right? That's, no one knows the area of that, but what we would do in reality is we divide it up into smaller areas. Like there's two rectangles there. Here's another rectangle. Let me see, you know what that would be. And then two triangles. So we'd have area 1, area 2, area 3, area 4, and area 5. Now, we know the area of a square or a rectangle, and then we would just add all those up together, and we would get the area of that particular shape. So what I'll do is actually I'll clear that. Or maybe I'll just bring in another one. I'll just bring in another shape that we know. For example, the circle here, okay? I'll just move that up here. So I'd just like you to use your imagination. Pretend we don't know the area of a circle. It's hasn't been invented yet. And we want to find a way of calculating the area of it. So what we could do, I'll just do it in red line, is we could draw a square. It's not working there. Sorry. So we draw a square inside. We know the area of a square, but we don't know the area of a circle. Let's draw a square inside. Okay, so what we can say here is, I counted them up earlier. There's 1, 2, 3, 4, 5, 6, 7, about 7 squares, right? So well, let's write this down. So I just draw a line around this one. We don't need it anymore. So what we're looking for is the area of the circle. So I'll call it A0. That equals area of circle. But we don't know pi r squared, right? It hasn't been invented yet. So what we're going to do is we're going to look at the area. We know the area of that square. So that square is basically inside the circle. And that's, let's say, 7 blocks by 7 blocks. So we can say that we call it A1, right? We'd say A1 is equal to 7 multiplied by 7. So that's equal to 49 units, right? Each one of those units is, each one of those blocks, small squares, let's say, has an area of 1, okay? So we can say that, you know, let's call it delta A, just for, look, so we'll say delta A is equal to 1. Don't worry about the terminology for a while, we'll come back to that. So we'll say that A1, no, another way we could write that, we could say that is the summation of all those, right? But let's not get worried about terminology yet. Now let's draw another square. Just draw it like this. Now, if we look there, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 by 10, right? So A2 is equal to 10 by 10. That's equal to 100 units. Okay, so we can make the following statement. We can say that the area of the circle, well, it's greater than A1. We know that just from looking at it, and it's less than A2. So we can say that the area of our circle, just get rid of that, is greater than 49 and it's less than 100. Now, that's not brilliant, is it? Like, you know, that could be anything. It could be 52, could be 57, could be 99. We don't know. But at least it's a statement. It's a start, right? Now, let's go back up to this square now. Now, if you see all the shaded squares there, right? They're all the squares that are contained within the circle. And then you have the additional squares are the white ones, which contain some part of the circle. So again, we can write down the following statements. Let's say the shaded, let's call them A3, right? So I'll just put a line around this. So let's say that A3 is the shaded square. So A3, we can count them up. It's 1, 2, 3, 4, 5, 6 by, that's 8. So it's 48 plus 1, 2, 3, 4, 5, 6 plus 12, right? So that's equal to 60 units, okay? And now let's look at A4, which is the addition. So that's 60 plus all the white squares, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 27, 28. Yeah, plus 28. So that's equal to 88. Okay, I think I've done that correctly. I think so. It doesn't matter anyway. So now we can say that the area of the circle, well, it's less than 88 and it's greater than 60. Now that's a better approximation, now we're saying that the area of the circle is greater than 88 and it's greater than 60 is less than 88. So what I've done here is we started off with a very crude means. We used only two. We used one big square and one smaller square. And then what we did on our second attempt is we divided up the areas into smaller units, smaller little squares, right? And we found out that we had a more accurate approximation. Now the actual area of the circle is what? Pi r squared. So let's say that's the center of the circle. 1, 2, 3, 4, 5. So it's pi times 25, isn't it? Equals pi 5 to be squared. 25 multiplied by pi. 25 multiplied by pi equals 78.5. Okay, so that's the actual, but what we've done is we didn't know that, right? So we tried to have an approximation, okay? So what we have two limits. We have an upper limit, which in this case, the upper limit was 100 and the lower limit was 49. And in this case, the lower limit was 60 and the upper limit was 88. And by dividing, so the core idea here is by dividing up the areas into smaller and smaller little units, we get more and more accurate. Now, if I had an even finer mesh there, right, we get closer and closer and closer to 78.5, right? So that's the idea of that there. So we have two limits. We have an upper and a lower, and we want to somehow trap the area of the circle. And how we do that, if we made the grid smaller and smaller by bringing the upper and lower limits closer together, then they'd finally converge to the correct answer. And that's basically the core idea of integration as a summation. So now let's get on to the area under a graph, which is more, I suppose, what you're used to. Okay, so area under a graph. So I'll just bring that up. Let's draw a graph. So if we have some curve, I'll just do it in maybe black. So that's your curve. You say that's X and that's Y. Now what we're looking for here is, I'll just draw a line here. And let's say that's point A. I shall extend this a bit further. So what we're looking for here is the area that's bound by the x-axis, which is this line along the bottom, and the y-axis and the curve. So effectively, it's the area, I'll do it in lines, but I'll take it off then again, right? So it's this area, all the area under there, okay? That's what we're looking for. Okay, so let's look what we're going to do here in this case. Again, we don't have any formula for that, the area. So we're going to divide it up into small little units. And in this case, we're going to divide up into small little strips. So let's pick a point here, X. So if we go up X, we just draw a line up here, X straight up. And that's, let's say that's the point P. And then obviously there's a Y element to that as well. So let's say that's the Y coordinate. So we just have point P with the X and Y coordinate, right? Now, this is kind of the core, another kind of fundamental, let's say, element of integration is this notion of delta X. So we're going to do a very, very small strip. We're going to make a very small strip. So we're going to move over. No, I can't draw it that small, so I'm going to draw it a little bit bigger. So we'll come over a distance delta X. Don't worry about that yet. So I'm just going to draw another line here. And let's say that point is X plus delta X, right? So what I'm saying really is that the width of that strip is delta X, okay? Now, if this coordinate here is X plus delta X, let's call this the point Q. And just by, the same as we did before, we just draw a line across here. And let's say that coordinate is Y plus delta Y. So that's our strip, okay? And whereas in the previous example with the circle, we had a unit. Each one of those small little squares was a unit. In this case, we're just going to call it delta A. Okay, so in other words, we're looking for A. So we call that A, right? A is the area under the graph between the line A, the y-axis, and the x-axis. So what we're going to do is we're going to look at this strip, okay? And now we don't even know the area of that strip. So what we're going to do, I'll just do it in a different color again, maybe pink. If I draw a dotted line across here, so what we're, sorry, the first thing I'm going to do is I'm going to show you exactly what we're looking for. So maybe if again, I'll just do it like this, right? Everything that's inside here, that's the strip, that's the area of the strip we're looking for. Okay, is that clear? If I had a pointer, I'd show you better, but that's what we're looking for. We want to get the area of that. Okay, just that strip. That's all we're going to look at for now. So I'll just take off those lines there again. But we don't know that because we don't have a formula for that, right? So what if we drew a dotted line across here, a dotted line up here, and a dotted line here, okay? And now we have two rectangles, okay? So I'll try and draw it, and I'll take it off again, if you don't mind. So let's do it with the purple line here. So first of all, we'll calculate the area of this square, which I'm sure you can see there, right? So that's one square. And the second square will be this. Sorry, not square, rectangle. Okay, so we're going to look at the areas of those two rectangles. So the first one, the width is delta x. So it's this distance here, right? That's delta x by the height. And the height here of this rectangle is just y, right? So in other words, that's y. So we have the height, we have the thing. We can say that that's y delta x, right? Now, we know just from looking at it that that's smaller than delta a, right? So we could say that that's smaller than delta a. And similarly, we can look at the second rectangle that I said, so that's the one that goes from here to here, right? So let's look at that. Again, the width is still delta x, this delta x, right? But the height this time is y plus delta y. So we can say that y plus delta y times delta x. So that's the area. This is the area of the bigger rectangle, and this is the area of the smaller rectangle. One is an underestimation and one is an overestimation of what we're looking for, which is delta A. Now, when I said a while ago about summation and limits, right? Let's introduce limits. So now we have an underestimation and an overestimation for the strip, but that's not what we're looking for. We're looking for the total area, right? So let's introduce the idea of limits. So we're looking for the sum of all the strips. Okay, and we just define that. So what we're looking for is A is equal to the sum, this is just in mathematical terms, from x equals 0, that's here, right? That's x equals 0, up as far as x equals A. What are we looking for? The sum of all the delta A's. So in other words, what we're looking at one strip, right? And then we're just going to add them up, all those strips together. If we add up all the strips, we'll get the area we're looking for. So let's just apply that to the first. Let's apply that back up here, right? So then we can just rewrite this as the sum from x equals A to x equals 0 of y delta x is less than A. I'm not going to write all that out again, okay? I'll just write down A. So all I'm doing here, I'm just applying this notation to this equation, okay? So in other words, this equation up here, I'll call it equation A. That's just for delta A, right? But what we're going to write down here now, this is where we've switched over, and now we're looking for the area. So we're just summing up all the strips. So that's equal to the summation x equals A, I should say it right, from x equals 0 to x equals A of y plus delta y times delta x. Okay, right. Let's just write that out again. I'm just going to drop the x equals, right, just to make it shorter. So it's the sum from 0 to A of y delta x. We say that's less than A. And again, the sum A to 0. Let's just multiply this out. So it's y delta y plus delta y delta x. Is that okay? I just multiplied this in to those two, okay? Now, remember earlier I was saying that, we start off with a very crude, and if the smaller and smaller we make those divisions, the more accurate our answer. So in this case, if delta x, if we keep making delta x smaller and smaller and smaller, we'll get a more accurate answer. We'll get the correct answer, okay? So now I've already introduced summation. This is where I introduced summation. Now I'm going to introduce limits, right? So well, I introduced limits already because it's a and 0, but now we're just going to make that strip 0. So this is where we bring in, so what we want to do is make delta x go to 0. It'll never go to 0, but we want to make it smaller. So that's how you do it, right? So let's go back up to this equation here, right? And I'm going to rewrite that here, but introducing the limits, right? So now we're going to say that a is equal to the limit as delta x approaches 0. Is that okay? I presume it is. And then we just put in that summation, x equals a, x equals 0 of, sorry, I'm just going to stop there a second. I'm just going to go back, not do that yet. Apologies if you've written it down. So let's go back and look at this. I'm just going to change color to red. Let's go back and look at this equation, okay? Now, if delta x goes to 0, if this gets smaller and smaller, this width here, okay? If that gets smaller, well, also delta y is going to get smaller as well, because if you move, let's say if you move this in, then delta y is going to come. So delta x goes in, delta y is going to go in, right? Now, if delta x is very, very small and delta y is very, very small, well, then delta y multiplied by delta x is going to be incredibly small. It's going to be so small that we say, we forget about it, right? It's just insignificant. That's kind of a fundamental statement to make in integration, but there's a reason for it. So now let's go back and look at this line again. So we're saying that then, you can write this out. So let's bring in the limits as well. So if that goes to 0, you're left with the statement. I'll write it. Actually, I'll go back to the original color. So then let's rewrite that line as a. So I'm rewriting this line now. 0, y, delta x less than a, and then a, 0, y. Sorry, I should have put in, that should have been delta x there. I just, I'm sure some of you spotted that. Okay, so that's y, delta x. So now, if we look here, we have the same on both sides. So then we can make the statement, but we have to write it like this, that a equals that, right? But it equals that only when delta x goes to 0. So this is how we write it. We say that a equals the limit as delta x goes to 0 of x equals a, x equals 0, y delta x, right? That's the answer. That's the answer for the area, which it basically, as I said already, all that is adding up all the strips. We calculate the area of one strip and we add them up. But the key part is that we make delta x incredibly small. In other words, bring it as close to 0 as possible. Now that's a very wordy, it's a very long thing to write out. So this is where we introduce the squiggly line, as we call it, right? So we just say this bit here, I'll just do it in red maybe. This bit, we introduce the squiggly line, right? So I'll do it in red actually. We'll say that a equals the integral between a and 0 of y dx. Don't worry about dx, it's just delta x. Instead of writing delta x, we write. So that's the same. So that's it, right? That's probably what you're familiar with. So the area under any curve is the integral of y dx between the limits. And in this case, the limit was a here, right? And 0. Okay? Now, that was for a curve between a and 0. Let's move on. I'll just give you a second to write that down just in case. We can also do it between any points. So I think we're okay. If anyone has missed a bit, let us know and I'll come back to it later. So I go on to the next page. Okay, so let's look at the example where you have an x and y. So we have y and x. I do a different color, blue. Let's say we have a curve like that and we want to get the area between A and B. Now, looking at it, what we did the last time, we got the total area between this line this line, and this line. So in this case, we were looking for the area. This is the area we're looking for. So you could actually say, I'll do it in different. Let me see, gray. That's the area of this minus the area, I'll do it in a different color, pink, minus this area, isn't it? That would give you that. So that's what we're looking for, right? So in this case, this is A. So in this case, we can say that A, let's do it out normally, is equal to the area of, like I just said, B, between B and 0 of y dx, right? Minus the integral between A and 0 of y dx. Now we can rewrite that in simpler form as A is equal to the integral of B, between B and A of y dx. And if any of this is not clear, it will become clearer later when we do a few examples. Okay, so that's the first part complete. That's just kind of the introduction as integration, as a summation. So the next thing is actually on the curriculum. Well, whilst this isn't on the curriculum, it's vitally important to understand integration. The second part we're going to do, I'll do a new page. So this is the first part on the curriculum. It's integration as reverse. Integration as reverse of differentiation. Okay, so if we start with a given function, let's look. I could call it ax. I could call it anything, but in this case, I suppose you all know the notation dy dx is equal to f prime of x if you've done differentiation already. Okay, so in this case, I'm just going to call what I'm starting with f prime of x, right? So if we start with a given function f prime of x and ask what function or function f of x would have f prime x as their derivative. Okay. So again, I hate all these wordy kind of descriptions. Let's give an example. Let's say we start with some function f of x, right? Let's say f of x is equal to 3x squared plus 7x. Oh, there's an x there. 7x minus 2. Now, if we get dy dx of that, so dy dx or equals f prime of x, right? We all know how to differentiate it. Presumably you've done that already. That's equal to 6x plus 7. If you haven't done it, I really don't have time to go through it today, but I'd say you probably did. I think it's, I don't know, I'd say most of you have done differentiation. So that's that, right? So basically that's the difference. If we differentiate this, we get this, okay? Now, so let's write that out, okay? Let's say f of x is equal to 3x squared plus 7x minus 2. So my x's are looking like 8s. It's the correction on this one, and I'll just change pens. 3x squared plus 7x minus 2. Okay, and then we have the f prime of x that we just worked out. F prime of x is equal to 6x plus 7. Change pen. So what we did with this one is we differentiated it. So right down here, differentiate. So we took this function, we differentiated it, and we got this function. Now, what we're looking at is that the reverse process. So let's do it this way. So if we start off with 6x plus 7, and we get the let's say we anti-differentiate, that's the term they use, right? Anti-differentiate, then we get this term, right? But let's just look at another function. Say if f of x, in this case, I'll do it in a different color, doesn't matter. F of x equal to 3x squared plus 7x minus 11, let's say, right? If we differentiated that, well, that's also equal to 6x plus 7. So we can see there's a problem, right? It doesn't seem to matter what's happening here after 3x squared plus 7. We seem to be getting 6x plus 7, right? basically what's happening is the constant term is disappearing when we differentiate, right? So in this case, like if that was minus 11 there, and if we differentiated it, if this was minus 11, we'd still get 6x plus 7, right? So there's a problem then when we anti-differentiate. How do we get back to this, you know? It's easy to go this way, but there seems to be some issue to get back to this, okay? So what we can say, I made it to write this out. I'll write out, this is kind of a definition, yeah, so it's important, I suppose. If f of x is an antiderivative of f prime x, and then so is f of x plus c. I'm introducing the c for any constant c, right? Sorry, let's make that a bit different. C. The c is very important in this, right? So it doesn't matter what we start with. If it was minus 555 and we differentiate it, we'd still get 6x plus 7. So what we're saying is, and now I know what you're all thinking, I put in 6x plus 7 and then you go back the other way to get 3x squared plus 7x minus 2. Well, you're not going to get it. That's because I must introduce something else now, right? So also I'm just going to introduce one other thing before I get on to another definition. If f prime of x, right, is equal to x to the n for n not equal to minus 1, the reason for that, we'll come to that later, then f of x is equal to x to the power of n plus 1 all over n plus 1 plus c. Okay, so let's go back up here, right? So we started with 6x, right? So 6x is to the power of 1, right? So 6x to the power of 1 plus 1 is 6x squared, and then divided by n plus 1, which is divided by 1 plus 1 is 2. So then we can see how we get from that term 6x to 3x squared, right? And the 7, similarly, is x to the power of 0. So then the 7 becomes 7x using this formula. So to maybe clarify the C a bit better, we'll introduce the notion of definite and indefinite integrals. And again, I know if this is new to you, this whole notion of integration, some of this might be a bit too much, but once I start doing examples later, it'll become a lot clearer, okay? So first of all, the indefinite integral, right? Indefinite. So if we started with something like f of x dx, what I mean by indefinite is that there's no limits applied, right? So there's nothing here or here. But again, once I read out, that becomes a new function. We just call it capital F of x, but we must put in plus c, right? That's the antiderivative there. And that's just a constant. So if it's an indefinite integral, your solution, you can see this is what you're doing is you're integrating some function f of x, and you're getting some function as your answer plus c. Well, your solution is another function. Again, this will all become clearer later. Solution is another function. Okay, now in the definite integral, so that would be something like this between b and a. So there are limits. The upper limit is b, the lower limit is a, of some function f of x dx. Well, that's equal to capital F, again, we use the same notation, and you fill in, basically you get a new function. So if you look at the first part, it was f of x, you fill in for b, and then you subtract it from a. We kind of introduced that earlier, remember when we had the area under the curve, when we had the b and the a, and we subtracted b from a. That's the same thing that we're doing here. So this solution in this case, well, that's a number. Okay, that's section 1 complete. So now we'll move on to section 2 time-wise. We're doing okay, yeah. So the plan really this morning is to go through the course, the curriculum before
Sorry.
break. Yeah.
Sorry, apologies, Mark. I wonder,
fine.
I've got a question in from the audience here, and I'm just not sure what it is. It says, what is the long line before the F? I'm just not sure what that means.
Oh, the long line before the F is the integral sign. It's the integration. So I'll go back a page there, right? That's a good question. At the very start here, where I was defining integration, right? This line here, so I'll do a circle around that, maybe. So in other words, that's the integral between a and 0. And what does that actually mean? Well, it means the same as this. It means the sum between a and 0 as delta x gets smaller and smaller. Now, we could write out this all the time, but it's quite long, right? So that squiggly line is just known as the integral, right? So it's the integral. Basically, what we're saying there, a is the integral of y dx between a and 0. So it's an area. It's the y, it's the height multiplied by the width. In this case, y is the height, dx is the width, and it's the sum of all the small strips between a and 0. So that squiggly line, someone I suppose never done integration before, yeah, my apologies. That squiggly line represents the sum between 0 and a as delta x tends to 0. Is that okay, Eamon?
I think so. It makes sense to me.
Okay.
I'm just wondering if who submitted that question could say if that makes sense to them. Please.
It's just the fundamental definition of integration. You know, the integration is basically the summation of small strips, adding them all together to get the area what you're looking for, and then it's the summation of all the strips as that delta x, so the width of the strips gets smaller and smaller, and that squiggly line just represents the sum as x between a and 0 as the delta x goes to 0. It's just a notation, okay? But again,
yes.
as we do more and more examples, I'm sure it'll become clear, because again, 86% of you have never done this before, which is quite high. But look, once we start doing examples, I'm sure it'll become clear. You know, so far, all I've done is introduced the background to integration. So now we'll get into the actual, you know, solving some examples. You know.
That's perfect, Mark. Thank you.
Okay, so integration using tables is the next bit, right? Okay. So A, right? There's only, as they say there at the curriculum at the start, there was only 4 that you need to know. So the first one is the integral of any power, x to the any power, right? So that's a polynomial, isn't it? So that's equal to x to the power of n plus 1 all over n plus 1. But again, this is indefinite, so we have to always put in plus c. So if you're not given limits, you must put in plus c. Okay, so b is a to the power of x dx. You don't need to learn these. These are in your log tables. All there, okay? So a to the power of x, that's defined as a to the power of x divided by the log of a plus c. C, the third one you need to know, is the sine of ax dx. So again, what this represents really, again, just to be clear, right? So you're given the curve with sine of ax, so that could be anything like that, right? And you're asking for the area underneath that curve. So again, that's the y coordinate, which is the sine ax, and then dx is the little strip, and you're adding all them together to get the area under the curve, right? So that's defined as 1 over a minus 1 over a cosine ax plus c. Again, you don't need to know this. It's already in the tables. I suppose you should know where to find them. And then the final one is the integral of cosine ax dx And that's 1 over a sine ax plus c. So again, you can see that sine goes to cosine there in c, and indeed cosine becomes sine, and it's 1 over a, which is the number with the x, right? And just be careful with the minus. That's the only one to be careful with. Sine goes to minus cosine, but cosine goes to plus sine. Just a little thing. Now, I can write them down here. I think this is quite important, but that's quite easy actually, right? So we'll just call it the rules of integration. There's only two. So the first one is if you have a function with c, let's call it, look, this could be anything, it could be f, but I'd call it in this case u, right? So c times that dx, right? If you had any function like that, well, that becomes, it simplifies as c. You can bring the c, basically what you're doing is just bringing the c outside the squiggly line, right? The integral of u of x. Sorry, I'll turn off that again. U of x dx. Okay. So I'll give you an example then, right? So for example, if you had something like the integral of 5 times the cosine of 4x dx, well, that's equal to, you just bring the 5 outside. It's 5 times cosine 4x dx. Okay, so in other words, the 5 isn't impacted by the integral. And the second rule is if you have a function, let's say u of x. What I mean by u of x, that could be like, say, 4x squared plus 7x plus 3, right? And vx then is the next one, plus or minus v of x. V of x could be like cosine of 3x, for example, right? And let's say all that times dx. Well, that becomes, just to simplify, it becomes u of x dx plus or minus the integral of v of x dx. For example, if you had an integral like this, 4x squared plus cosine of x dx, well, you can rewrite that as equals the integral of 4x squared dx plus the integral of cosine of x dx. Okay, so there's 4 things. There's only 4 different types that you need to know. That's them, right? And then there's the rules of integration. The rules of integration, they're not essential, but they can make things a little bit easier. When you get a big complex kind of equation that you need to integrate, you can just use those rules to simplify it. So I'll just do some examples, right? So for A, I'll just change the pen. Don't like writing in red. So A, for example, that was the first one, which was x to the power of n. So let's say we had an integral like this, x squared plus 3 dx. So that's equal to, let's use the first rule of integration there. So that becomes the integral of x squared dx plus integral of 3 dx. Okay.
Sorry, Mark. I'm sorry to interrupt you again. I've got a question in about the previous slide.
Yeah.
And it was, what is under the second fraction?
Oh, the log, the natural log. Sorry, that's L n. Okay. So it's log of a, natural log. It's in the, I think that's the way they say it in the tables as well.
It is, yes. Thank you, Mark.
Yeah.
That's
all right. Yes, Lin. Lin, I think they call it, or Lin or whatever, but no, the natural log of a. Okay. Right. So that's the first one, right? So do you remember when we had a while ago? I'll write it down here again. The integral of, so what we said the integral of x to the power of n dx becomes x to the power of n plus 1 all over n plus 1 plus c, right? So in this case here, right, I'll rewrite this. So looking at the first part, the x squared becomes x to the power, I'll write it out slowly, x to the 2 plus 1 all over 2 plus 1 plus c, right? We call it c1 here in this case, right? Plus, let's look at the second one. So in this case, it's x to the power of 0, okay? Because x to the power of 0 is 1, isn't it? Okay, so in this case, the x is 0. So that becomes 3 times x to the power of 0 plus 1 is, so I actually write it out, x to the power of 0, that's what we started with. So in other words, you could write this as, you could even bring the 3 outside, right? X to the power of 0 dx. Okay, they're the same, they're equivalent. So that becomes 3 to the power, x to the power 1 plus 1 all over 0 plus 1 plus, we call it C2, right? So this becomes x squared over 2, isn't it? Am I right? Sorry, hold on a second. X cubed all over 3 plus C1 plus 3x. Because x is 0 plus 1 is 1 and 0 plus 1 is 1. So it's 3x, right? Plus C2. But C1 and C2 are both constants. So we add two constants together, we get a constant. So the answer here is x cubed over 3 plus 3x plus C, right? We could call it anything. We could call it W, but look, we just use C. It's a constant. So that's what we started with. We integrated, and that's our answer. Okay, and that's indefinite. So when it's indefinite, if there's no limits here and here, you must put in plus C, okay? So let's look at the second one. So it's B. So it's the integral of 2 to the power of x dx. Well, that's just straight from definition. It's equal to 2 to the power of x all over the natural log of 2 plus C. Okay, don't forget the C. You lose marks. And then let's do the final one, which is just C and D, right? It's an example incorporating both C and D. So let's say we're asked to integrate, and in this case, let's put in some limits between pi over 3 and 0. And let's say it's cosine of x plus 3 times the sine of x. Okay, dx. So in this case, the a is 1 in both cases because the previous definitions, we had sine ax and cosine ax. In this case, look, there's nothing with the x, so it's 1, right? Just to make that clear. So using our formula, cosine goes to sine, so it's sine of x. And then it's the 3, it's minus 3. Sine goes to minus cosine of x. So, but in this case, the a is 1, so it's 1 over 1. So it's just minus 3 times cosine of x. And then our limits, pi over 3 and 0, okay? This is just a way of writing it. You can do it the same way. I think it makes sense. So we've already integrated cosine. Cosine becomes sine. Sine becomes minus cosine, right? So we've already done the integration. Now we just fill in for pi over 3, okay? So I'll just draw that up here. So filling in first for pi over 3, you have sine pi over 3 minus 3 times cosine pi over 3. Okay. This is getting back to the FB minus the F of A, right? If you remember that from earlier. And then it's minus and filling in for 0. So it's, let me see, it's minus sine of 0 minus 3 times the cosine of 0. Now working all that out, right? I'm not going to get into all the trigonometry, is root of 3 over 2 minus 3 over 2, because it's 3 times a half, minus the sine of 0 is 0, and the cosine of 0 is 0. So it's, or sorry, cosine of 0 is 1, so it's minus 3. And then working all that out, you'll get up with 3 plus the square root of 3 all over 2. So there, this part's section, the second section, right, integration using tables, is usually the part A in the exam, and it'll just give you something like, you know, integrate that or integrate this and get the answer, right? So if you have a definite, so if you have limits, your answer will be a number like this, right? But if you don't have limits, your answer will be another function. And when you have another function, put in plus C. Okay. So now that's the second part complete. Time-wise, we're doing okay. So the third element is areas by integration. Which is effectively the very first thing I talked about this morning was calculating the area under a curve. So that's what we're going to do. So there's 5 scenarios in this, okay? So I go through them. So I suppose just to talk about it, integration was originally introduced to find the area under a curve. That's why we use integration. Okay, so let's say A, first example. So you have your X and your Y coordinate, and you have a curve. Okay, and you want to find the area under the curve between A and B. So in this case, the area, we talk about positive and negative in a minute. That's the area we want, right? And this curve is defined as y is equal to f of x. What does that mean? For any value of x, y is equal to some function of x, okay? So in this case, we know that the area, we've already done it, right, is equal to the integral between b and a f of x dx. Okay, and this is for curve above the x axis. Okay, case one. Second case. Oh, I should have done that the other way. So that's x and that's y. Okay, what if the curve is underneath the x-axis, and this is A, and this is B, and this is the area we want. In this case, the area will be negative, okay? And we'll see why. So the area in this case, again, is A is equal to the integral between B and A. What I mean by that is, like, you know, for example, if you come along here for some value of x, the x will be positive, but the y will be a negative value. Might be -4, and that might be 7 or something like that, right? So in this case, it's f of x dx again. And this will return a negative value. This will return a negative value. For example, it could be -16, right? But the area is always positive. So if you end up with, say, an answer like -8, well, then you just know that the area is equal to 8, okay? Because you can't have a negative area. Okay, so the third example, what if you have a curve like this? Oh, I'll do that again. That's your x and your y-axis. Maybe do a different color. Say if you had a curve like that, and you were asked to find the area between A and B. Now, just looking at the drawing, first of all, you know that this curve will be positive, right? So if you calculate that area, it'll be positive, and this area will be negative. When I say area negative, what I should say is the value that will return will be negative. Okay, now, if you did this right, you would get the wrong answer if you just did it using this formula. And the reason is because part of it is positive, part of the answer is positive, and part of the answer is negative. So they'll somehow cancel each other out. Now, if this was symmetrical about the x-axis, then your answer would be 0, because the area above where you might say might be minus or might be +10, and below, obviously, due to similarity, be -10. And if you added them together, you'll get 0. I might do an example later where I'll show you that, right? So in this case, what you do, and it's very important, and it's very important to remember, is you must find out where the curve crosses the x-axis, right? So let in y equals 0 into your function, and then you'll find out that. So in this case, your area is equal to the integral between c and a, f of x dx, plus the integral between b and c, f of x dx. Okay, where y is equal to f of x. So don't get too confused with that. That's just, you know, y is some function of x. That's all that is. Okay. Let's do one more. I'll go on to the next page. I'll give you a minute just to finish that. So in this case, like, again, look, we're looking at the limits. It's between a and c. The first part is this area, right? So that this relates to this, and this area relates to that. That's all that is, okay? So we calculated the areas separately. So if it crosses the axis, always remember, calculate above the axis separately and calculate below the axis separately, and then add your two answers together, okay? Because if you don't, if you just did here, like a equals the integral between b and a of f of x dx, you'd get the wrong answer. The areas would cancel each other out. Okay. So the fourth part, D, is this. They could just throw what, because there's not a whole lot to ask in integration, they somehow throw, you know, I suppose wobblers really, you know, just to kind of, you know, test you. So I think they did this one year. They asked, say that was your curve. They asked you to calculate the area here, right? So that's your y-axis, and that's your x-axis, right? So again, what we're looking for, that's positive. We're looking for that area. So in this instance, they're asking for the area between, let's say, it doesn't matter actually, A and B. So that's the area between A and B and the y-axis. Before it was always the x-axis, now it's the y-axis. So you just actually swap things around. You just say A is equal to the integral between B and A as usual. But in this case, it's f of y dy. Before it was the area was f of x dx. Now it's just f of y dy. So what would you do in an exam? Say if you had a question like, or if you had say, I don't know, y is equal to 4x squared plus 7x, right? I made it difficult for myself here. Actually, what you do is you put, let's just say it's 4x, right? So in this case, it's f of y we're looking for. So it's, you just switch it around and you say that, you know, before y is equal to f of x, wasn't it? But in this case, it's x is equal to f of y. So we're looking for the y, sorry, the x in this case. So in this case, x is equal to y over 4. So in other words, x is equal to, your f of y here would be y over 4. So your area would be a is equal to the integral between b and a, y over 4 dy. I hope that's clear. So in other words, usually that's the normal form, right? Y is equal to 4 of x. But when you're doing over the y-axis, just switch it around. Put the x to the left and put everything else to the right. And then you'll see that's your function then, right? And the final one then, E, is the case where you have two functions. For example, you could have I'll do it a different color. You could have a curve like that. And you could have another curve going like that. Okay. So in this case, we're looking for this area. Okay. So let's call this y is equal to f2 of x, right? This is only just notation. I could call it wx or px, it doesn't matter. And let's say the blue curve there is y is equal to f of 1x. Now, in this case, so sorry, I should find out that's b, and look, a is here, right? Okay. In this case, what you need to do, the first thing, you don't know a and b. Usually in the exams, they'll say, you know, find the point of intersection. So to find the point of intersection, the first thing you do is you let f2 of x equal to f1 of x, right? So that could be 4x squared, you know, plus 3x on one side and 2x plus 7x on the other side, right? Let them equal, and then you'll find out, you'll solve for x, and then you'll be able to find out the limits. So you'll find this point and this point, right, by simultaneous equations or what have you, okay? Then once you have your 2 points, you can find out that the area, so in this case, the area, I'll do it in pink, right? The area is the area under the blue curve, right? So maybe I'll just draw it like this. I hope you can see that. So it's the area under the blue curve minus, I'll do it in a different color, purple, minus the area, minus this area, isn't it? Okay, so it's the area under the blue curve minus the area under the red curve. And if you subtract them, then you'll get this area, gray area here. Okay, so first of all, it's the blue curve, which in our case is y is equal to f1 of x. So that's the area of b, a, f of 1 of x dx minus the area under the red curve, which is defined by f of 2 of x dx between b and a. Okay, so f of 2 is the red curve, so I just call that red, and that's blue. Okay, there's one more thing to do, right? And then we've done the whole curriculum, and it's very quick, so I may as well do it. and then we'll take a break. So the fourth one, right, is the average value of a function over an interval. I apologize for the writing. It's actually, there's a lag in it, so I can't actually see what I'm writing. So that's why it's a bit not brilliant. Okay, so that's just a definition. Might even be given in the tables, I'm not sure. If it's not that difficult to remember anyway. So let's just say, it's just a definition. F bar is equal to 1 over b minus a, the integral between b and a of f of x dx. Again, if you've never done integration, thinking, what is he on about here, right? Basically, this is just, it returns a number. It's basically the average height over a given interval, and the interval is a and b. So if you have some function f of x could be 4x squared plus 3x plus 7, right? And you want to find, maybe I'll just do an example, and then that'll finish up the curriculum really, right? So say if we have f of x is equal to x squared, x squared plus 1. Simple, right? So another very important part of integration actually is being able to graph, because in the last few years, they've always asked you to graph or, create a graph. So it's very important to be, when you see something like f of x is equal to x squared plus 1, is be able to draw it. So let's draw it together, okay? So let's draw a big graph so we can see it. So you have x and y. Let's go, let's say 2, 4, 6, 8, 10. It's really important to be able to do this, right? So maybe we take a bit of time doing it. 2, 4, 6, 8, 10, 12, 14, we'd say, right? 16, let's go 16. Okay, so when x is equal to 0, we know that y is equal to 1, don't we? Is that correct? When x is equal to 0, y is equal to 1. So I'll do it in a different color here. So when x is equal to 0, let's double check that. So when x is equal to 0, we fill in 0, 0 squared plus 1, so y is equal to 1. So when x is equal to 0, that means here is 0, y is equal to 1. That's a point on the graph. We have 1 point, right? Now, when when x is equal to 1, y is equal to 2, isn't it? So that's a point. So 1, 2. So now we have 2 points in the graph. When x is equal to 2, y is equal to 5, isn't it? 2, 4, yeah, 5. So that's a point. Let's say when x is equal to 4, 4 squared is 16, plus 1 is 17. So that's 16, 17. That's actually up here, isn't it? Okay, let's just go back. Say that when x is equal to 3, 3 squared is 9, plus 1 is 10. So 3, 10, that's a point. So this is your curve, right? Something like that. That's not perfect, right? But it's not bad. So you have to be able to draw a curve. So that's the curve, right, for that. That's x squared plus 1. So what that's now asking us is, I'll just change the color, is between 0, which is here, and x is 0, and 3, which is here. So let's just draw that. Okay, that's 0 and 3. It's asking us for the average height, right? So what's the average height of this portion of the curve? I'll just do it in a different color. Maybe I can do it in a thicker color. I don't know. I'm trying. I'll do it in purple. So over this section of the curve here, right? So just this section, it's asking us for the average height. So we know that the height here is 1, at the bottom right it's 0, and we know that the height here is 10, right? But wants to know what's the average height over the curve. So in this case, we just use our formula. So it's asking, let's say the question is, I'll write it here, find f bar between 0 and 3. Okay, so we just use the formula. It's just f bar is equal to 1 over 3 minus 0, and then the integral between 3 and 0 of x squared plus 1 dx. Okay, so let's work that out. It's equal to a third, and then I like to do square brackets like this. x squared becomes x cubed over 3, and 1 becomes x, correct? And then that's between 3 and 0. So filling that out, you get f bar, so that's equal to 1/3. Let's fill in for 3 first of all. So it's 3 to be cubed all over 3 plus 3 minus, now filling in for 0, 0 cubed all over 3 plus 0. Okay, so that's equal to 1/3 into 27 over 3 plus, let's say 3 is 9 over 3, isn't it? Minus, that's 0, isn't it? 0, 0, yeah, 0. So that's working all that out. Actually, made that, doesn't matter. Equals 1/3 of 36 over 3, which is 36 divided by 9. So f bar is equal to 4. That's your answer. So what we're saying there is the average height, and that's 4. The average height of that curve over that range between 0 and 3. Now, if you had a different range, obviously, if you had it over 8, then your average height would go up and you'd have a different average height. So that completes the curriculum, right? After the break, I'm going to go through past exam papers. And as I said, if some of that was a bit too heavy, probably was, if you never did integration before, then I think, just stop sharing the screen there. You know, the examples should make it clearer and should make it a bit easier. So now I'll hand back to Eamon there just to take the break.
Okay. Hi, everybody. It's 11:10 now. Should we go for a 10-minute break? Mark, do you think that's okay?
That's fine. 10 minutes back.
Okay. So we'll meet back here at 20 past. So
okay.
Okay.
See you later. Bye.
See you in a while. Hello, everybody, and welcome back to the second part of the integration tutorial. Just a quick little reminder, if by now you haven't got your log tables open, I recommend that you have your log tables open on page 26. There's a lot of useful things in there that Mark is going to be referring to, and you'll need them in your exam anyway. Okay, over to you. So again, Mark.
Thanks, Eamon. I noticed there during the break, I just read some of the comments on the questions and answer. Please keep coming in with your questions. Brian and Eamon are doing a stellar job. They're answering most of them, you know. So if there's any doubts or something is unclear, please use that. So I suppose before I go on there to doing the exam questions, right, I just want to kind of summarize everything, because I'm just kind of conscious of the fact that most of you haven't done integration before. So it's going to be brief. It all started off as we had an area. We couldn't calculate the area because the area was too complex. What we did is we divided it up into smaller areas, which we knew. You remember that kind of funny thing I did with the rectangles and the triangle? And we divide up into a number of rectangles and triangles whose areas we knew, and then we summed them together. Now, it was quite easy with the straight line shape. When we got to the circle, we had a curve. The circle is basically a curve. And when we started off with just, you know, the crude 1 square bigger, 1 square smaller, we found that solution wasn't very accurate. And when then we came up with a mesh or a grid, which was a refinement, right? The term is refinement of our original, let's say, estimation. We found that the answers were coming a bit closer. In other words, we knew what the answer was, whatever it was, say 78, and we had an 80 and a 60. And the more and more you refine that mesh or make it smaller, you get closer and closer to the answer. So your lower limit and your upper limit come closer and closer together. The next thing then is that we looked at the area under a graph. And what we did in this case is we took a series of very small rectangles, and they were rectangles. And we said that one was an underestimation of that delta A and one was an overestimation of the delta A. And then what we did is we summed all those strips. And then we thought about what we did earlier, and we found that if you made the strips smaller and smaller, you get a more and more accurate answer. So that delta X and that delta represents a very small amount, almost zero, but not quite zero, as Brian expertly put in one of the answers, right? Making that smaller and smaller. So then we introduced the idea of the limit as delta X approaches 0. So we summed up all the strips with incredibly thin delta X, in other words, the width along the bottom. And then we summed all them together and we got our area. And again, as someone said, what is the squiggly line? The squiggly line basically is the summation of all the parts between the limits A and 0 as that delta x, in other words, the width of the strip, it tends to 0. In other words, it's very, very, very small. And then we looked at integration as the reverse of differentiation. So I suppose we all know what differentiation is. Most of you have probably done it. So basically what we were just saying there is that integration, well, that's the reverse process. So what you do to a function to get its derivative, then you get the derivative and you do something to it to get back to the start. That's called anti-differentiation or integration, right? So we went through that, and then we looked at the definite and the indefinite integrals. And the important thing here is that if you get an indefinite integral, in other words, if there's no limits like a and b or b and a, then your answer is a solution. Or sorry, your solution is another function, and you must put in plus c, right? And then you had a definite integral, and your solution is a number. The third thing was using integration, using the tables, right? There was only 4. There was x to the power of n, a to the power of x, sine of ax, and cosine ax. And the solutions are given in the log tables. And then as part of that was the rules of integration. So we had c to the, like say, c multiplied by ux. So you can just bring the c outside the squiggly line, as we're going to call it from now on. And we did a few examples of that. The third part was areas by integration, where we looked at a curve above the x-axis, a curve below the y-axis. One returns a positive area, one returns a negative area. Obviously, the negative area is just the solution that's returned is actually obviously a positive area. Then we looked at where you have one part of the curve above the x-axis, one part below the y-axis. Similarly, that could be on the y-axis, right? And you look at those separately. So if a curve crosses an axis, straight away alarm bells go off. You must find that point and calculate the areas separately. And the fourth one then was just about the y-axis. So in other words, instead of fx dx, you have fy dy. Be careful with that. And then the final one was calculating the area between two curves. And what's important in that is that you get the points of intersection of the two curves, and then then you have your limits. So in this case, you're not given the limits. You have to find out what the limits are. And the fourth part then was just the average value of a function over an interval. That was what we just did before the break, right? Again, I think the best thing now to do is to go back and do some past papers and some other examples, and that'll give you an idea. So really, I suppose with geometry of the line 3 weeks ago, I felt that, you know, really understanding it was the way forward and would help you in the exams. With integration, certainly the first 2 bits, part 0 and part 1 that I did, was really giving you the idea of what the background to integration and using it. Don't forget that, because a few years ago they did, I'll actually draw it, they gave a kind of a curve like this, but it actually wasn't a curve. I just from memory now, I can't remember, but it was something like this, right? And they asked you to find the area underneath that curve. I think they called it a curve as well, but trying to catch you out, I suppose. And I saw some people were looking at that as like, oh, f of x, and they're trying to figure out what is the area. We know that, you know, we know that area is equal to f of x. Sorry, I just did that again. F of x dx. So we need to find our limits. Grand, we have our limits. That's 5. That's 0. Right, we can do that. That's 5. That's 0. We don't have the curve. A definition of that curve. What is it? What could it be? You know, we need f of x. So some people tried to figure out what the curve was. Like, was it 7x squared plus 3x plus 2x plus minus pi, whatever. But actually, all you had to do was this. Look, divide that up into a series of 1, 2, 3, 4 rectangles. That was let's say that's 2. That was, you know, 2. That was 3. Let's say, and that was 2, right? It was just adding up the areas. So the area was equal to the area of 1 plus area of 2 plus area of 3 plus area of 4, right? So it was that simple. But if you didn't really understand the background to integration and, you know, what integration is, it's dividing up a complex area into smaller areas and then summing them. That gives you the answer. So that's why I think it's important. Yes, you must understand integration when you're going into the exams, because just relying solely on being able to regurgitate what you did on past papers may not be enough, because I think there's only 4 things to know in integration. They can, you know, maybe, you know, try to expand it a bit, or maybe try to put in a few tricks. So let's do 2019. And it was paper 1, question 4. I think I have it here. I'll just bring it up. It's this one. Okay, not exactly straight, but it doesn't matter. You can see it there, right? So the first part was quite simple there. I have to X that, don't I? Yeah, okay. So part A, I presume you can read it. Yeah, so I'll just write it out again anyways. Find the integral of 4x cubed. Oh, sorry, it's minus, isn't it? Minus 6x plus 10. Now, straight away, we see that's an indefinite integral. Why is it indefinite? Because there's no limits given, right? Okay, so going back, it's even in the log tables, right? Here you see that's a polynomial. You know what a polynomial is. You say, we just write it out. X to the power, I write it on the side, x to the power of n, the integral of that goes to, let's say, x to the power of n plus 1 over n plus 1. So let's just apply that to this, okay? So then we say that the integral, we can call it I, you can call it whatever you want, is equal to, let's look at the first part, that goes to 4 x to the power of 3 plus 1, which is 4. 3 was the original one, right? 3 plus 1 all over 4. Minus, let's say 6x. Minus 6x, that's obviously 6x to the power of 1, right? So it's 1 plus 1, so that becomes 6x squared all over n plus 1. N in this case is 1, so it's 1 plus 1 is 2. Plus 10, and 10, again, when you see a 10, you'll just know in the exams anyway by doing more and more examples. 10 could be written as 10 to the x to the power of 0, so that becomes 10 to the power x power of 0. So in this case, n is equal to 0, so 10 becomes 10x. Okay, and because this is indefinite, we have to put in c. So let's write that out nicer. It becomes, the 4's cancelled, becomes x to the power of 4 minus 3x squared plus 10x plus c. So that's your answer. Now that was pretty straightforward. Just check, did I get that before? Yeah, x power 4 minus 3x squared plus 10x plus c. That's your part A question done, okay? The second part of the question is part of the graph of a cubic f of x is shown below the graph, not the scale, right? The graph cuts the x-axis at the 3 points A, 2, 0, B, and C. Given that f prime of x is equal to 6x squared minus 54x plus 109, show that f of x equals 2x cubed minus 27x squared plus 109x minus 26, minus 126. So this case now, right, we're given the derivative. So we must find f of x. So we know that we must do the antiderivative. So let's write it down. So f of x, what we're looking for, is equal to the integral of f prime of x. So again, this is the important bit on this. Do you remember before where I had the table with the antiderivative and the derivative, right? So in this case, we're starting off with f prime of x. We're starting off with the derivative, but what we want to find is the antiderivative, the function, right? So in other words, if we have some function f of x and you differentiate it, you'll get f prime of x. But in this case, we're starting with the derivative and we must go back to the original function. So we must get the antiderivative, and we do that by integration. So that's, in this case, is equal to the integral of f prime of x. Let's write it out. So we're given f prime of x is equal to 6x squared minus 54x plus 109 dx. Now, this is an indefinite integral. Remember that. So then let's write that out again. Let's start integrating. So before, like we did before, look, 6x squared becomes 2x cubed. Again, how does it become that? The x squared plus 1 is x cubed divided by 3, because it's 2 plus 1, and then the 6 divided by 3 becomes 2, okay? Minus 27x squared. And again, if some people can't see how 54x becomes 27x squared, by doing these, they become second nature. So what I did there, again, look, just to go a little bit slower, 54x becomes 54 times, 54x is 54x to the power of 1. So in this case, n is 1. So going back up to this equation here, x to the 1 becomes x to the 1 plus 1 divided by 2. The 54 divided by 2 becomes 27. So that's minus 27x squared. And similarly, it's plus 109x. Because it's indefinite, put in the c. Now, What are we asked? 2x cubed minus 27x squared plus 109x minus 126. But we don't have that, right? We have 2x cubed minus 27x squared plus 109x plus c. We don't have minus 126. So how can we get rid of the c? We must solve for c, right? But how do we do that? Well, we're told that the point 2, 0, this point here, is on the curve, right? So this is f of x now, just to be clear. This is f of x. This is your curve. So we started off with f prime. That's actually the tangent at any point on the curve, right? If you do differentiation, I'll give you it next week, you'll know about that. So now we have a definition for the curve, but we have this unknown c, and we need to get rid of that. So we just basically plug in for c, right? So we know that 2, 0 is on the curve, is on f of x, right? So then we just say, filling in, that's the x, that's the y. So let's fill in for x and y. In this case, look, y is equal to f of x, but that's just, you should just know that at this stage, right? So in other words, the y coordinate at any point in this curve is a function of x, and it's a function of 2x cubed minus 27x squared plus 109x plus c. But we know that 2, 0 is on the curve. So let's go back up here. So we fill in f of x, well, that's equal to 0, isn't it? Because that's 0, y is 0. And then fill in 2 for x. So it's 2 times 2 cubed. Sorry, there's something funny going on there. Let's rub that out. So it's 2 times 2 cubed minus 27 times 2 squared plus 109 times 2 plus c. So we've all known values except the c, and we solve for c. And look, I won't waste your time, but c ends up being 126 there, okay? So filling back in for c, sorry, it's equal to minus 126. So filling back in, then we can say that f of x is equal to 2x cubed minus 27x squared plus 109x minus 126. Okay, that's part B done. So in this case, we were given the derivative. And do you remember at the very start, we had this issue where I think someone even asked the question, where did minus 11 come from? It was just showing that it doesn't matter what you start with your derivative. Sorry, no matter what, if you had fx and you derive it, then the last function just goes away. So in this case, we didn't know what the last function was. So we had to use information that was given to find out what it was. I could explain it a bit further, but like it might take too much time. But say if that was minus 125, all that would effectively do is actually shift the curve down. So the curve would still have the same shape, but would it be in a different location? So the constant just, it moves the curve around. So it still have the same shape, like that would be the cubic shape, right? But the constant would move it up and down. And if you can imagine, it doesn't matter where that curve is, for any point on the x-axis, the tangent will always be the same. So that's why the f prime of x is the same at any given x, because the curve just moves up and down, right? And that's the explanation for that. So in this case, we were given the tangent, or the derivative, prime of x, and we were asked to find out the equation for the curve. So first of all, we kind of got a kind of a general, this is the kind of general equation for that curve in any location. But then that location was tied down by, we know that the curve crosses the x-axis at the point 2 is equal to 0. Then using that information, we found out what c was. So c no longer became an unknown, it became minus 126. Is that clear? Any questions, send them in on the Q&A there, and we'll move on to the third part of that question is just, it's finding the coordinates of points B and C. It's nothing really to do with integration, so I'm not going to do it here this morning. So we go on to 2018. So I'll just write down here 2018, and I'll bring in the paper. It's this one. It's straighter this time, not exactly straight. I'll try and get it straight. No, it's fine anyway, right? So it's question 6. And it asks, parts of the graph of the function h of x equals x and k of x equals x cubed for x real number are shown in the diagram below. And part A is, let the coordinates of the point of intersection of the graph, sorry, find the coordinates of the points of intersection of the graphs of the two functions. Okay, so we have h of x, I'll write it out, h of x is equal to x, and k of x is equal to x cubed. So this was what I was telling you about earlier about manipulation of graphs and all that. They seem to throw it in a lot with integration, and it is an important part. So like this, the first part here is nothing to do with integration, but it asks you to find the coordinates, right? So if you have two curves, in this case, one is a line, but a line is a curve, I suppose, and you want to find the points of intersection of those lines, well, then you just let one equal the other. So in this case, we'd say that x is equal to, I'll just turn that off there now again, this. So we say that x equals x cubed. Okay, so x equals 0 obviously is an answer. So we can see straight away, look, that 0, 0 is the coordinate, right? But that's not what they're asking for, isn't it? It says, what does it say? Find the coordinates of the point of intersection of the graphs of the two functions. Well, it is. I suppose 0, 0 is an intersection, yes. So 0, 0 is an answer, right? So let's just cancel that out. So let's cancel one x against the other, right? And that becomes 1 is equal to x squared. So the solution for that is x is equal to plus or minus 1, isn't it? Pretty straightforward. You know, I could say it's the square root of 1, which is 1. So x is equal to plus or minus 1 is the solution. So when x is equal to plus or minus 1, we have to find out what the y values are. So we have the x coordinates. So in other words, we know that that's minus 1. And we also know that this is plus 1. But we don't have the y coordinates yet. So we just plug that back in. But it's obvious, right? This is the line h is equal to the line y equals x, isn't it? So the x coordinate equals the y coordinate. So it's quite obvious. So for x equals minus 1, y is equal to minus 1. And when x is equals 1, y is equal to plus 1. So we just say y is equal to plus or minus 1 as well. So the coordinates then, we just write out. So the coordinate, the answer is the coordinates are minus 1, and 1, 1. Not entirely true because 0, 0 as well. So we put in 0, 0. So there's 3. Okay. So that's the first part done. That's A. So it's the second part of that question is find the total area enclosed between the graphs of the two functions. So it's asking us for, I'll just do it in pink, find this area. So we call that A, right? So it's A, looking for A. Right. Now looking at this, we can see that it's symmetrical, can't we? We can see that, so let's call this A1. Let's call this A2. So we can say that if we calculate one of those, doesn't matter, but in this case, we're going to say that A is equal to A1 plus A2, but it's actually equal to 2 times A1. Okay, you can do this. There's nothing wrong with doing this. You're using your knowledge, your ability to see that that's symmetrical, therefore those areas are the same, right? So let's calculate the area of A1. So what is it? So A1, right, is equal to, it's the area, I'll do it in red first of all, it's the area of the red triangle minus, I'll do it in blue, minus this area. Is that okay? So again, it's the area, it's between, so we have already got our limits, it's 0 and 1, right? It's obvious once you draw it out what the limits are. So it's the area beneath hx, right, minus the area below kx, between 0 and 1. So we say that A1 is equal to the area, now A1 is just the area, but I've shown here is equal to the area between 1 and 0, that's 0, of x dx, that's hx, right, minus the area between 1 and 0 of kx, and kx is x cubed dx. Okay, that's the important bit in this question, is setting it up. Okay, so we're calculating A1. That's this area here that I just did in pink, whatever that color is, right? So again, we'll just integrate that. So x becomes, we know now at this stage, once you do loads of examples, that becomes x squared all over 2 between 1 and 0 minus x cubed becomes x to the 4 all over 4 between 1 and 0. Okay, working that out, you get it's a half minus 0. But basically all you do is you fill in for 1 and you fill in for 0. So you fill in for 1, it's 1 to the power 1 squared is 1 over 2 minus 0. And then the second part is 1 over 4 minus 0. So a half minus a quarter is a quarter equals a quarter. So this area here, I'll just do it in a squiggly bits there, right? That area is equal to a quarter, but we're asked for the total area. So that's, we set up here that A is equal to 2 times A1. So here A is equal to, A equals 2 times 1/4 equals a half. And that's your answer. Okay? I think that's what I got. Yeah, okay, so that's right. Again, that's pretty much everything they can ask you under areas of integration, right? You know, using integration to calculate the area, because in this case, we knew that we're in this quadrant, so everything in this quadrant, or everything above the x-axis is positive, and that's negative. We could similarly have done A2, and we would have ended up with minus a quarter, but again, we know that you can't have a negative area, so it's a quarter and then 2. But we could have done it, if in this case, right, maybe we'll do it as a quick exercise. If you took the curve, right, between -1 and +1, so in other words, if you set up your area as the total, right, in other words, it would be so it's the xy is x dx between 1 and -1 minus the integral of let me see, yes, minus the integral between 1 and -1 of x cubed dx. If you did that, it's wrong. You would have come up with 0. Maybe we could do it out quickly here. I'll see what. So I'll do it out really quickly, right? And see that happens. A is equal to an integral of x dx, right? So that becomes x. I'll actually do it like this. X becomes x squared over 2. I'll actually bring this one in as well, and that becomes minus x to the power of 4 all over 4. So if we filled in for 1 and -1 here, we would get a half minus a quarter minus, so that's the first part there, half minus a quarter, correct, yeah, minus -1 to be squared is 1 all over 2, and then -1 to be the power of 4 is actually -1, so it's -4. So that becomes a half minus a quarter is a quarter, minus a half minus a quarter is minus a quarter, and that equals 0. Okay, so that's a good example of where we didn't look at where the curve crosses the x-axis, right? If we just jumped straight in and said, right, we need to get the area between +1 and -1, we would have got 0. Well, inside the exam, you'd know something was wrong anyway. So in a case like this, you could calculate them separately. Like we could have calculated A2, but it's exactly the same as A1. So by looking at that, we can say it's symmetrical. No, if it's not symmetrical, you do have to carry out the two lines separately. There's a third part to this question. So it's part 3. Oops. Part 3, right? It says, on the diagram on the previous page, use symmetry or otherwise to graph k minus 1. I thought this was a particularly nasty question, right? So k minus y, which is the inverse function of k. So k minus 1 to the power of x, or function of x, right, is actually, so kx, we'll just write, I'll write it out again, kx was equal to x cubed, right? So the inverse of that function is equal to x to the power of a third. Okay? Some people might have put down x to the power of -3. It's not, right? It's x to the 1 over 3, right? Or you could have done. So again, it just says graph it, right? Or use symmetry, right? So if you're ever asked to graph something, this is what I always do. So let's go back to this, right? So it's between 0 and 1. So let's get like a quarter or a half or 0.2, 0.4, 0.6, 0.8, and 1. That might be, so that's the 0.2, that's 0.4, that's 0.6, 0.8. So if we find out, the answers for that, okay? So let's write down maybe this is a good way of doing it. Let's say write down a series of x coordinates and see what the y coordinate corresponding one is. So for 0, if you fill in 0 here, it becomes 0. If you put in 0.2, I've worked this out already. 0.2, you get 0.58. 0.4, you get, I'll actually work it out there now. 0.4 xy 1/3 equals 0.74, we'd say. And let's say 0.8, right? 0.8, you get, what is it? 0.8 xy 1/3 equals 0.93. And then obviously if you put in 1, you'll get 1, right? So using those values, right? So I just write down here so I have it myself. 0.4 is 0.74 and 0.8 is 0.93. Let's go back to our graph. That's all we've done. They've asked us just, the question again was on diagram on the previous page, use symmetry otherwise to draw the graph of k inverse minus 1, right? The inverse function of k. Okay, so I do it in maybe I'll just roll out some things that we have here already. Okay, and maybe just report all that because that's to do with the previous. Okay, so let's just put in dots, right? So 1 point is 0, 0. We calculated that. I'll go back again. So 0. That's a point on our new graph. When at 0.2, so that's 0.2, it's 0.58. So that's 0.2, 0.4, 0.5, 0.5. It's about here, right? And then when x is equal to 0.4, we got 0.74. 0.4 is 0.6, 0.7, so about there. Okay, and then 0.8, we got 0.9. Am I doing the right thing here? 0.6, 0.1, 2, 3, 4, 5. Yeah, 0.93 is about here. So your curve looks something like that. You can see what's happening anyway, right? And obviously by symmetry, that's what they say. Look, your curve is going to go something like that. Now I didn't draw it very well there, right? But that's the idea. So that was part 3. It was just asking you to graph that, okay? But again, like I did earlier there, right? I just did I could have similarly done another one here for x and y, and then just did 0, minus 0.2, minus 0.4, minus 0.8, and you would have got the values here for y and just plot them. So that's 2018 done. Again, any questions, send them onto the Q&A and we'll have a look at them.
There was one quick question, sorry, Mark.
Yeah.
Are you using the function k to the power of -1 x to get the x and y values?
Yes, sorry, I should have said that. So y is equal to x to the third, right? That's equal to k inverse x. Yeah. Is that okay? So yeah, that's y there. Look, y is equal to k inverse x.
Yes, that's great. Thanks, Mark.
All right. So we'll do 2017. Okay, so question 6 on 2017 was the graph of the function g of x is equal to e to the power of x, where x is an element of R, between 0 and 1, is shown on the diagram below. On the same diagram, draw the graph of h of x e to the power of minus x, right, in the domain 0 or x between 0 and 1. So again, that's the same as we had before, right? Let's just do, our x coordinates. Hold on. So you have your, this is the way I do it. I think it's the best way to do it as well, right? So you just do your x, your y. Let's put in when x equals 0, 0.2. So quite similar to the 2018 question, 0.6, 0.8, and 1. So, you can use your calculator, right? So when x is equal to 0, e to the minus x, so y is equal to here, I'll just write down, make it clear this time, y is equal to e to the minus x. So when x is equal to 0, y is equal to 1. When x is equal to 0.2, y is equal to 0. 0.81. And then working your way down, right, you can use your calculator. I get 0.67, 0.55, 0.45, and 0.36. So let's graph them. So when x is equal to 0, that's here. Y is equal to 1. So it's the same as that point. When x is equal to 0.2, it's 0.81. So that's 0.2, 0.4, 0.6, 0.8, 0.81, both here, right? And 0.4 is 0.67. So that's 0.4, 0.6, 0.8, both here. 0.6 becomes 0.55, 0.55 roughly there. 0.8 becomes 0.45, both there. And 1 becomes 0.36, both there. So again, you'll excuse me now, I'll try my best to draw this. So it's something like that. Okay, not too bad. I'll make my dots bigger. Okay, so that was the first part done. Question A, simple, okay? Second part of that question, part B, was find the area enclosed by gx equals e to the x and hx, which is e to the minus x, and the line x is equal to 0.75. So again, you need to be able to draw that line. So it says, right, can I do it here? I can. Should have enough space. It's the find area between, gx, hx, and the line x equals 0.75. Right, so let's draw the line x equals 0.75. Let's do it in purple. Okay, so that's x equals 0.75 is roughly there, right? So again, we'll try our best to draw a straight line here now. Okay, not too bad. So that's the line x equals 0.75 there, right? X is equal to 0.75. Basically, that's saying that for any coordinate there, right, the x is always going to be 0.75. So this is the area we're looking for. That's our A, we'll call it. Right, have we got our limits? Yes. Have we got our curves? Yes. It's subtracting one curve from another curve. So again, let's labor over this because it's important. We're going to look at two areas and subtract one from the other. So the first area, I'll just draw outside it, is this area. I drew a rhombus, hold on, sorry. So I'll try that. So it's this area here, right? Okay, that's our first area. That's the area of the line under gx and the x-axis and our limits. Our limits in this case are 0 and 0.75, right? That's our limits, 0 and 0.75. That's what we're worried about. So that's the we call that area 1, right? I did it in blue line. I'll do the other one in, let's say, the gray line. And we have to subtract this area from it. Sorry about that. We'll do this area. And that'll be our area 2. And that's kind of key to setting up all these questions, right? When you have two graphs, or two curves, I should say, and you want to find the area between them. So we call that area 2. So in this case, we say that our area, the area we're looking for, which is this area here, area is equal to the area 1, which is the blue one there, right? Minus area 2. So let's write it out. Area 1 we know is the integral between 0.75 and 0 of e to the power of x. Okay, dx minus the integral between 0.75 and 0 e to the minus x dx. Okay, that's clear, I hope. So we've just set up, that's setting up our solution. So then we just integrate and we have our solution. So the integral of e to the x, you can get it from your log tables, is e to the x. 0.750 minus, and the integral of minus e to the x, be a little bit careful with this, that becomes minus 1, because it's given in the tables Yeah, it gives you e to the ax, right? And e to the x goes to e to the x, but e to the ax becomes 1 over, I'll write it out here, right? So I'll just write it in a little box. E to the ax, if you integrate that, that becomes, let's say, 1 over a e to the ax. So in this case, our a is -1. So it becomes -1 times e to the minus x. And then our limits are 0.75 and 0. So working that out then, I do it slowly because with the e's is always tricky, right? It's e to the 0.75 minus e to the power of 0. All we're doing is filling in for the x, right? 0.75 and 0. So that's the first part. Then we look at the second part, which is this one, minus, that actually becomes minus, that minus becomes plus, right? Plus e to the minus 0.75 minus e to the power of 0. And that's actually minus 0, right, to be technical. Okay, so working that out, you get, fill in the values, is 2.117 minus e to the power of 0, which you all know is 1, plus e to the minus 75 is 0.472. I got this using my calculator, by the way, minus 1. And then you can figure out that that's equal to 0.59 units. Okay. That's the answer to that. Now, if you look at it, then you can see that that's, if that's 2, right? That's 1. Then the length of this triangle is about, about 1. And that distance is 1. So half times 1 times 1, the area of the triangle, it's 0.5. So you know that you've more or less the right answer. So again, I'd always do that as well in an exam. Look at your answer, 0.59. Does it look right? It does. I mean, if you've got an answer there of 27, that's not the area of that triangle because the base of the triangle is about 1. It's 1.2, right? And the height is 1. So, half multiplied by 1.2 by 0.1 is 0.6. So then you'd know that that's, you're pretty, I think you've got the right answer. Okay. So we go back to 2014 next.
Apologies, Mark. I've got 2 questions coming from a student here. Well, 2 different questions.
Yeah.
The first one is the dx multiplying by e to the power of minus? And the other one is, why did the minus change to plus?
Yeah. Okay. So again, just looking at maybe this equation here, right? The e to the x is the y coordinate of the x. So for our function, I think that's a good question, right? Because like gx, right? So let's look at the first part. Gx, right, is equal to e to the x. Well, that's y, right? That's the y coordinate is equal to e to the x. So what's that saying? That's saying for if you come over at 1 and you plug 1 into e, then you get the y coordinate. Do you know what I mean? So if you put in 1 here, right? So if you're for x equals 1, which is here, you plug that into e to the 1, then you'll get there, right? Which is about 2.117. That's what that means. That's what gx means. The gx is a function of the x to give you the y coordinate. And I think some people do. I missed it for years until I finally dawned on me what it was. That's what that means. So in this case here, when the guy was asking about, the ex to dx, well, effectively, that's your strips again. That's your height. Your height is ex, and your dx is some really narrow strip width, right? And that's what the ex. So you are effectively multiplying it, but it's just an integration technique. The integration technique then transforms that e to the x. Now, e to the x obviously is a bad example here because when you integrate e to the x, it becomes e to the x. So what you're doing then, this is the integration bit. You've gone from there to there, right? You're forgetting about your squiggly lines after that. All you're doing now is you're filling in for 0.75 and 0, which is what we did here, 0.75 and 0. You subtracted one from the other. And the second part of that question, Eamon, was again, the minus and the plus. So again, here, it's also, remember at the very start, it's the FB minus the FA. The FB in this case was A1 and the FB was A2, right? So it's the larger area minus the smaller area to get the area in between. So you're subtracting one from the other. That's where I get that minus, right? So that's A1. So that's A1. This is A1 and this is A2. You're subtracting one from the other. So it's A1. That's A1 there. That's A2. Okay, so you're subtracting A1 from A2. Where I got the plus was, there was a -1 here. So that -1 I brought out, so a minus times a minus is a plus. That's where that came from, okay? I could have left the minuses inside, but I think that's easier to do it the way I did it. Okay, is that clear, Eamon? If it's clear to you, maybe it's clear to the lads as well.
It's clear to me, Mark. I haven't got any feedback from the student, but I think it's clear to me anyway.
All right. Okay.
Thanks, Mark.
So I'll move on there. 2014, right? Part A was quite simple. It says find 5 times the cosine of 3x dx. Okay, so remember the very first rule of integration, you bring the 5 outside, so that becomes 5 times the integral of the cosine of 3x dx. And we know we have it in our tables, the cosine of ax, in this case a is 3, right? So what we do is 5 times 1/3, so it's 1 over a, and in this case a, as I said, a is 3, times the sine of 3x. And that becomes 5 over 3 sine 3x. Correct answer? Not quite. This is an indefinite integral. There's no limits, so don't forget at this point you're plus c. You lose 5 marks, simple 5 marks for that, right? So, or whatever, 2 marks, whatever, you know. So that's your answer. Don't forget the c. If it's an indefinite integral, put in c. Okay, the second part of that question was, it said the slope of the tangent of a curve y equals f of x. So it says the slope of this curve, right, at each point xy, at xy is 2x minus 2. So it just says, I'll read it out again. The slope of the tangent to a curve y equals fx at each point x and y is 2x minus 2. The minute you hear tangent, you know that that's the derivative. So let's write down straight away dy dx equals f prime of x equals 2x minus 2. So we were given that. We were told, again, just to be clear, I'll read out the slope of the tangent to a curve y equals f of x. At each point x and y is 2x minus 2. We were just given 2x minus 2. But you should be able to see straight away tangent. That means that's the differentiation. So that's 2x minus 2. And it says, the second part of this, it says the curve cuts the x-axis. So curve cuts x-axis at, sorry about the writing, I can't see what I'm writing, at minus 2, 0. Okay, it says, and the question is, find f of x. So what are we given in this case? Just 2 things, actually. It's a load of writing and a load of words, but all you're given is, you're given the tangent, which is 2x minus 2. So I'll write down tangent. You're given the tangent and you're told that the line cuts the x-axis at minus 2, 0. And then it says find f of x. So f prime of x, let's write it out again, is equal to 2x minus 2. Now we want to find f of x, but we know from earlier on f of x is equal to the integral of f prime of x dx. So in our case, f prime of x, we know it, so it's the integral of 2x minus 2 dx. So by the techniques we've done already, we say that f of x is equal to 2x becomes 2x squared divided by 2, which actually becomes x squared. And minus 2, integrate that, it becomes 2x plus c. Okay? But we don't want c, we want to get rid of c. So we now know that minus 2, 0 is on the curve, right? We're told that that's on the curve. So we just plug that in, basically that's the x, that's the y. So you fill in that 0, so y 0 equals minus 2. So it's minus 2 to be squared, minus 2, what's your minuses now here, plus c. So that's 0 is equal to minus 2 to be squared is 4, isn't it? Am I right there? Minus 2 to be squared is 4, yeah. Minus 2 times minus 2 is plus 4, isn't it? I'm doing it all right here, plus c, yeah. So then from that we say that c is equal to minus 8. So then you just plug that back in up here, and you find out that your final answer is f of x equals x squared minus 2x minus 8. So that's kind of a classic question, really, where they give you the tangent and they ask you to find the curve. So, you know, but again, it could be, as I said, that could be in any curve. You know, with the plus C, it could be any curve, but it's tied down in by the you know, they tell you that curve cuts the x-axis at -2. Okay, and there's a second part to that.
Apologies, Mark. Just before you move on to that, there's a question about part A. Where did the 1/3 come from when you integrated the cos 3x?
Okay, let's go right back to the definitions. I went too far, didn't I? Yeah, so we go back to here. There it is. Just a definition there, right? So it was a cosine, wasn't it? If you have cosine of ax, in our case here, it was 3. So cosine of ax dx becomes 1/a sine of ax. So in our case, it was 1/3 sine 3x plus c. So it's just a definition. It's in the log tables. Okay, Eamon?
Yes, Mark, that's great. I don't know if that's actually in the log tables. I can't see it. I'm pretty sure it used to be years ago, but I can't see it now.
Maybe it's not. Yeah. So look, it's easy to learn anyway.
It's one of those ones you need to practice.
Yeah, yeah. Sorry, I gave wrong information. It's not in the log tables. You're right, Eamon. So it's quite easy anyway, right? It's just that, but in the log tables, it does give cosine and sine. So at least you know the cosine goes to a positive sign, and you see that sine goes to a negative cosine. So if you have the a in there, it just becomes a fraction of that. So it's sine. So I say sine 5x. Go to your tables. You see, oh, sine goes to minus cosine, but because it's 5x, it's -1/5 times the cosine of 5x. So yeah, learn them off. It's not difficult, I think. Okay, so the third part of that question was find the average value. So I'll write it out. It says find the average. I can't even see it. Oh yeah, find the average. Sorry, apologies for writing. I just something's gone funny with the Zoom. Find the average value f, right, over the interval 0 less than or equal to x less than or equal to 3. Okay, so it's the last one, right? So we'll just pick up that f of x equal to x squared minus 2x minus 8. So it was linked to that question. So we have f of x. So f of x is equal to x squared minus 2x minus 8. So find the average value of f over that interval, okay? So we know that the fourth part of our curriculum this morning, right, said that f bar is equal to 1/b minus a, by definition, right, the integral between b and a of f of x dx. Okay, that was the definition, right? Is that in the log tables? I don't think so. So that's just something you have to learn off. Correct me if I'm wrong. I don't think it is. Okay, so that's just the definition. Okay, so filling in for here, our b in this case is a and b, right? Are 0 and 3, and our f of x we have. So we have everything we need. So we just plug in the values. So it's 1/3 minus 0 into the integral between 3 and 0. And then it's x squared minus 2x minus 8 dx. So that's equal to 1/3. And we can integrate straight away. X squared becomes x cubed over 3. Minus 2x becomes I'll write it out, minus 2 times x squared over 2 minus 8x. Between 3 and 0. So we can work that out, write out neater maybe. So it's 1/3 into x cubed over 3 minus x squared, the 2's cancel, minus x squared minus 8x, 3 and 0. So filling in for 3 and 0 into that, you'll bring the 1/3 outside anyway. So we have to 1/3 into, that's 3 times 3 cubed is 27/3 minus 9 minus 24. And then fill in for the 0. So it's 0 minus 0 minus 0. Okay, so it's 1/3. Just put a 3 underneath the line, see what happens. So So it becomes, sorry, 27 over 3 divided by 3 is 9. So the 9, that they cancel, don't they? 9 minus 9, so it's minus 24. That's equal to minus 8. So that's the answer to that. Okay, so F bar is equal to that. Okay, that was 2014. Let's go back to 2013. I'll just leave that there a second for everyone to write down. So that the average height over that function between 0 and 3 was minus 8. So it's similar to a question we did earlier. So 2013, we might finish up on this one maybe. So the first part was between 2 and 0, 12 e to the power of 3x dx. Just said evaluate that, right? And it said give your answer in the form of this. So it's a e to the b minus 1. Okay, so first thing I do here is I get rid of the 12. So it becomes 12 times integral between 2 and 0 e to the 3x dx. Okay, so now that becomes 12. And so it's e to the power of 3x, so that becomes 1/3 e to the 3x. And then between the limits of 2 and 0. So the third can come out straight away, so it becomes 4. And then e to the 3 times 6, so it's e to the power of 6 minus e to the power of 3 times 0. I just did that. Look. 3 times 0 is 0, we know that. Okay, that's not quite in the form that they wanted, so it's 4 into e to the power of 6, and e to the power of 0 is 1. So that's your answer. Okay, so a little bit tricky with the e's, and again, that's if the E1, the E1 is definitely in the book or in the log tables. It says e to the power of ax. So let's write that down. The key to that is e to the power of ax, right? That becomes, when you integrate it, it becomes 1 over a e to the power of ax. So what the power stays the same, it's just the whatever numbers with the x comes outside. Okay. Okay, so the last one would take nearly 10 minutes. So it's part C of that question. Part B was actually to do with differentiation, so I'll move on. It says draw the graphs, draw y equals 4x and y equals x cubed. Okay, that was the first part of the question, right? Draw the graphs. So in the domain minus 2 less than or equal to x less than or equal to 2. So we'll draw it. So I'd say that's 1, that's 2. Probably that's not a good idea to do it like that, and then I do it a different way. So that's 1, that's 2. And I'd say that's 2, 4, 6, 8, 10, 12. Okay, so again, I do this like before, right? Y equals 4x. That's quite easy to draw, isn't it? So when x is equal to 0, y is equal to 0. So that's a point on, we call this, look, we call that ux, right? We call this vx. Okay, so let's draw that. So when x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to 4. But similarly, if it was minus 1, it would be minus 4, wouldn't it? So that would be here. And then for 2, it becomes 8. And then 2 over here, so that's minus 2, minus 1. That becomes minus 8. That's here. So I'll try and draw a straight line through that there now. Hopefully this works. Not too bad. Okay, so that's the line y equals 4x, right? So, and then similarly, we could do y equals x cubed, okay? So it says between 0, so between 0, minus 2 and plus 2. So at 0, it's 0, right? So that's another point in the line, right? So when x is equal to minus 2, well, y is equal to minus 8, isn't it? So 2, 8, roughly there, right? And similarly, 2, it'll be equal to 8 as well. No, it's a little bit off. But anyway, they put in 1 becomes minus 1 and plus 1, right? So I'm just a little bit against time here. So it'll become there, be like 1, something like that. Okay, that's pretty badly drawn, right? But it'll give you an idea anyway. And you know, you must find out what the intersection points are. So let's find out what the intersection points are. The intersection points are important now because the second question says find the area bound by this, right? So that's what we want to find. So the first part was just draw it. We did that. So now we need to find that area. So the intersection, to find intersection points, which is this point here and this point here, we let them equal each other. So we'd say that 4x is equal to x cubed. And we get that, you know, obviously 0, 0 is a point, so we'll cancel that out and that cancel out. So you get that x is equal, or x squared is equal to 4, right? And there's two obviously answers for that. So x is equal to plus or minus 2. Now, the way we drew it, we kind of knew that anyway, right? Oh, I drew that pretty badly there, but x equals plus or minus 2. So when x equals plus or minus 2, y is equal to 4x. It's 4 times that, so it's plus or minus 8. So we know then that the intersection points here are minus 2, minus 8. Again, the graph is a little bit wonky, right? Because it's difficult to draw on the iPad. And again, this point up here is 2, 8. So what have we done so far? We've drawn the graph. We've got the intersection points on the graph, okay? I have a question coming in, Eamon, do I? No, no question. Okay.
Yes, you do. You've got.
Oh, yeah.
If you don't have time, that's fine. But how did you get the coordinates for the line and curve?
Oh, yeah. Just I did it really quickly here. Sorry, but like I said, when say let's look at the first part, right? I'll just do the line. When x is equal to 0, y is equal to 0. So that's the first point. When x is equal to 1, y is equal to 4. So come over 1 and up 4. That's a point, right? And then when say y is equal to 2, sorry, when x is equal to 2, y is equal to 8. So that's the point. Now, the line isn't perfectly on it, but they're the 2 points, this one and this one, right? Similarly, if you put in minus 2, you'll get minus 2 would be 4. And then, sorry, minus 2 would be 8 here, and minus 1 would be minus 4. Okay? So it's just plugging in the values, Eamon, for 0, 1, and 2. That's what they asked for, between minus 2 and plus 2. And then minus 1 and minus 2. Plugging them into this. And like if I had time, I would have done it like this, the x and the y, right? And 0, 1, 2, and then got the corresponding values. 0, 1 is 4, and that's 8. Okay? And similarly, I would have done it for the y equals x cubed. That's where I would have got the points. Okay?
Perfect.
I'll move on
That's
there,
great.
because I just
Thanks,
want to do
Mark.
the important integration part here. So the second part then is find that area, right? So that area is equal to, again, we just draw it quickly there now with the pink. I'm just going to do this quadrant, and we know by symmetry the area, so that's A1, we'll say, and that's A2. The area we're looking for is equal to A1, 1 plus A2, which is actually equal to 2 times A1. Similarly, like because it's symmetrical, right? So we're going to find the area, right? So the area, again, like before, is the area of the triangle there minus this area, which is the area under the curve. Okay? So it'll be the big area, which is the red line. So that's equal to 4x dx between, now we know the x coordinate is 2, between 2 and 0, limit I should say. So that's 2. Again, that's drawn badly there, right? But look, that's 2. Minus the integral between 2 and 0 of the other one, which is x cubed dx. Okay, so working all that out, like before, we get 4. So you integrate 4x, you get 4x squared over 2 between 2 and 0. Keep it simple. Minus the integral of x to the power of 4 all over 4 between 2 and 0. Okay, so again, that's just the area under the red line minus the area under the blue line, right? And bound by the x-axis. So working that out, you get bring the 2 outside, and that becomes x squared over 2, isn't it? Sorry, that becomes x squared minus 1/4 times x to the power of 4 between 2 and 0. So working all that out, right, you get 2 into 4 minus 0 minus 1/4 into 16 minus 0. I'm working out it, you get 8 minus 4 equals 4. Now that's the area of the upper, in the upper quadrant, but we say that 2 is equal to, A is equal to 2 times that. So the area is equal to 2 times 4 equals 8. Okay, that's it. So we've done a good few examples there. I would encourage you to do more yourselves, right? There's plenty of places where you can find them. Again, so going back over it again, right? There's the curriculum. There's only 4 things. Recognize integration as a reverse process of differentiation. We've definitely done that. Use integration to find the average value of a function over an interval. We've done that using that formula. And it says then integrate the sums, differences, and constant multiples of the functions of the form x to the power of a to the power of x, sine ax, and cosine x. We've done that. And the final part was determine areas of plane regions bounded by polynomials and exponential curves. And that's what we've done there with most of the examples. So Eamon, that's pretty much it. I think I've covered everything. For the last 5 minutes. If there's any questions, we can answer them, you know. So I'll pass back to you, Eamon.
Brilliant, Mark. Thank you very much. It was a very good presentation and lots of examples. I don't see any questions coming in from anybody right now at the moment. Give them another few seconds. But I suppose the important thing for integration and calculus is to do a lot of practice. And try and understand what you're doing at the same time. Keep an eye on that. But there's a lot of things that you really need to practice and use the log tables and go over past exam papers. And I just wanted to share actually that screen there. There was they formed the log tables on page 26, but also have a look at, if you haven't done already, the examinations.ie website where there's all the past papers, and also there's the solutions and marking schemes that they use. So very useful for your studies and to get good marks. So far, I don't have any questions coming in.
Okay, that's good.
From any of the students. So I think we'll say thank you very much, Mark, for a great presentation.
Thank you. And I wish all the students all the very best in the exams.
Brilliant. Thank you. Thank you, Mark. And next week we will have the differentiation tutorial, which is, of course, related to integration. As Mark mentioned there, integration can be seen, at least one way of looking at it is the reverse of differentiation. So for now, I think we still don't have any questions coming in. Any last minute questions? No, we're okay. So see you all next week for differentiation. Thank you, Mark.